our goal today. What are these guys called? Partial fractions, and how do we get them? Lots of examples. You guys ready? We're going to play with some math today. Not quite as many numbers as section 7.1 and 7.2, but still solving. What did you see me right here at the very, very bottom? Still technically solving systems, but there are going to be some creative approaches that might make it a little bit easier. And there is a bit of a systematic approach to it, maybe a bit more systematic, even to the tricks. But first of all, zeroing in on the example from yesterday. So at the very, very beginning of yesterday, we introduced section 7.4 by saying, hey, partial fractions are these, well, something to do with taking a put-together fraction that's been all combined, common denominators, all that jazz. And maybe some of you didn't realize what I was pointing to as to who the partial fractions actually are. In this example, who are the actual partial fractions? 2 over x plus 3 is one partial fraction, and negative 1 over x plus 2. Those are our partial fractions. Parts, partial. Fractions that combine and put together or can be combined by common denominators to be the original. Partial fractions, breaking a whole down into its smaller parts. So I gave an example yesterday because we were running out of time, and I was like, well, some of you might be able to start on homework, so let me show you a quick example of what's going on. And actually, I'm a little concerned that some of you didn't realize how far you could have actually gone in homework last night, which was actually around number 15, 16, something like that. So let me pull up homework to go ahead and show that to you. Just a couple of you every now and then in Google Classroom, I see something to the effect of you guys saying, I didn't know how to go farther. Now, if it was like the first night of homework, I would understand. Some sections, if it was the second night of homework, like vectors, I would still totally understand. But by the time that homework is usually due, unless it's something where I ask for 50 to 75%, guys, how often do I do examples in notes similar to homework? A lot. Now, do I do it like every single section of homework? No. But what is there in the book usually that can help you at least follow something? Examples in the actual section, and then if worse comes to worse, you can't find an example in the section, you can't find examples in our notes. Maybe you didn't take complete enough notes, so you couldn't find examples from class on the video online. Could you also look at an odd CalcChat solution to see if that can help you out? Okay, so you could look at the notes, you can look at the video online in case you missed something in notes or you don't know how we did what we did and you need to listen to me explain it again. You can look at examples in this section and odd examples, odd CalcChat solutions to see if that helps. But here's something I'm going to look at really quickly before we even go through the process of solving partial fractions. Now maybe you could have gotten a little confused on some of the vocab because we haven't finished all of it, but you could write and fill in the blank or make the blanks and fill in later. What was the first section, numbers 5 through 8? What was it asking you to do last night in homework? Match the decomposition. What did you see us do yesterday? Even though we didn't finish the entire example, that would help you in this problem, actually kind of starting back in the page before. Splitting up by factors or looking here and getting common denominators. Either way, as far as matching, in the first section of homework, you could have actually tried to match this way or that way. Yesterday, we got common denominators and saw that it matched that denominator. We didn't totally get the numerator until we had to do some extra work. So when you were looking in the homework last night, which you should have probably done, because it's always a good idea to at least start your homework, and I think some people were saying if you got through number 16, you're kind of halfway done as far as the numbers. Now, it does get harder past number 16, but as far as the numbers of problems. So right now, if I was to get common denominators, for instance, with this guy, wouldn't I have to multiply him by both of the other ones? And him by both of the other ones? And him by both of the other ones? Which of the fractions down below seems to match up with multiplying all three of these together and getting common denominators? Sure looks like this guy, difference of squares, x plus 2, x minus 2, and x. Wait a minute, hold on, so we could actually just factor and then match. Okay, so what happens when we factor this guy? We have an x minus 4, and then we have an x and an x. Which one seems to have, ooh, okay, that's a little weird. But maybe there's some sort of approach to this that I don't know quite yet. Because most of you would think, hey, let's do x, let's do x, let's do x minus 4. If you just went off yesterday, take the factors, make a fraction for each. But is it x and x? No. Does anybody know why it wouldn't be just x and x? It's the same. If they were both x, couldn't they just go together to be one single fraction? So the only difference, the only way to make it different is, could you have an x squared and could you have an x and still get a common denominator of? Yeah, because couldn't he multiply by him? Couldn't he multiply by him or 2 of him? Well, squared of him. And couldn't he multiply by x and x minus 4? These are the 3 possible denominators that could be combined to be that combined fraction down here, rational function. So I'm not going to finish off the other ones, although I think I just did the 2 even ones, so the odd ones are pretty obvious. But the beginning of homework was just saying, hey, how do you break it down, or how can you put it together and make it match? So what's going on in numbers 9 through 16? I had a few people yesterday that were like, I didn't know what they were asking. Write the form. Write the form. What's the difference between what you guys see here and what we saw at the beginning of notes yesterday when I said, hey, these are the partial fractions? The book had A's and B's, whereas this, thanks, Rachel, actual numbers. So these are the actual solutions. What do you think the ones with A's and B's are? The forms. Because the A and B isn't solved for yet. So maybe that answers some of your guys' question. And as far as the example right here, what are we supposed to be finding in this example? Write the, what do you think? Are we just getting the forms, or are we getting the actual partial fractions? Yeah, we're trying to get the actual partial fraction. So all of this work, we started off with the form. You have to start somewhere to say, hey, this guy can come from these guys. So breaking down into the form of the partial fractions is the beginning of the problem. We'll talk about that in the steps. But then the rest of the problem is actually trying to solve for what the actual partial fraction decomposition is. Decomposition, breaking down into partial fractions, solving for A and solving for B. As you guys were working through the example, who can or who thinks that they have some sort of explanation as to why, oh why, or how, oh how, I got this system to solve at the end? How did I get this system? What did I do starting from the beginning? What would you guys say? What's the very first thing I did after getting the form? Multiply both sides by the original denominator is one way of saying it. And I heard someone else say something interesting. Kyle, was it you? Not just the original, but the common denominator. If I was to get a common denominator, multiply by him. And what do you notice, or what did you notice happen when you multiplied? Just x plus 7. I'm left with numerators, but I can't just have a, because if I was to get a common denominator, the x minus 3 didn't matter, but who would need to get added in? The x plus 2. Or you can think when you distribute that whole lump, x minus 3's go away and x plus 2 remains. What happens when you distribute the whole lump to the b expression? The x minus 3 remains. So you can think of it as, oh, I'm getting common denominators, if that helps you. You could multiply by x plus 2 over x plus 2 and x minus 3 over x minus 3, and then all the denominators whoosh away. That's another way of thinking about it. Yeah, exactly. Why is this expression way easier than this one? No fractions, right? Okay, but what was hard here? Okay, pause, time out. What was hard over here when we were talking about complex numbers back in the day? You would see these, I think you saw one of these or two of these on homework, and you saw one or two on the test. What was hard about this? Two variables. I don't know, well, there's I, but I has a meaning, right? Isn't he the square root of -1? Oh, here, do you guys want to see a joke? Calculus got bored because they finished their test a little bit early. And I was looking at all my math jokes just to entertain them. Is this it? Here you go. Poor guy. Anyway, I got one laugh. But coming back, speaking of I, he has a meaning, right? Square root of -1, whether or not he exists is very confusing. But coming back, why do I have blue stuff on one side and green stuff on the other? One equation, it's impossible. It's not. one equation. This first part is of any complex number. We call it a real. You can say constant. It will be some sort of constant, but real. And if that's the real part, what's that part? Well, imaginary is the term I was looking for, right? So what's true on the other side? If this is also a complex number, what's the 11? Real. And what's the negative 5i? So what are you able to do sometimes based on what you've been given? Categorize the information. I'll take the real components, even though it's one equation, it's possible. Take the real components, the real had to come from the real. The imaginary had to come from the imaginary. Wait a minute, where'd the I go? Oh, silly me, should have been an I, right? But wait, what happens if both sides have an I? Say, well, didn't the negative 5 have to come from the b minus 2? Yeah, couldn't we have divided both sides by I and they reduced? You guys agree? So we could have written the I. Technically, they both had I's, but they do reduce the coefficients. So then we're able to say what is A and what is B. Now, how does that match up with what's over there? But first, Adam. Oh, did I not put a negative 5? Lame sauce. Can I not do math? Oh, I put my thingy through it. Oh, I thought it was a plus. Thank you, Adam. And Tony, and everyone else who was like, you can't do math. Some days I can't. Some days I can. So then coming back. What does that have to do with this? Real and imaginary and how I can categorize is similar to what's up here. But A's and B's aren't really my problem. I need to find A and B, but categories. What categories do I have on either side? X terms and constants. I mean, yeah, they're all real. But X terms and constants. So when I go ahead and distribute, I can say, hey, you're an X term, you're an X term, you're an X term. I put all my X terms together, and I actually took these two, AX plus BX. I factored out an X to say, well, A plus B must combine to be 1. I have a 1X over here, so my X terms get to be a category in and of themselves, or an equation in and of themselves. Like we ignored the I's, we're going to ignore the X's. Just looking at the coefficients. So I have one equation, 1 has to come from, 1X has to come from A plus B. But those are the X term, or that is the X term category. But what else do I have? A constant category. So negative 7, ooh, is that a negative? Oh, no, it's plus. It gets confusing when I put my circle over it. My 7 has to come from 2a minus 3b. So what do I do as soon as I have 2 equations and 2 unknowns? Solve the system. So solving the system, do you guys solve it? What did you do? Substitution, elimination? Did you do the R1, R2? Eliminating the A's? What did you guys do? Elimination? Did you multiply the top guy by negative 2? Well, we want the opposite sign to be able to add, because once you start subtracting, everything gets a little more confusing. So if you were to add down, you would end up with negative 5b equals 5. So b equals negative 1. Once we get one variable, what can we always do? Back substitute. You can go here or here or here or, let's go here. So plugging in, if that's negative 1, I have 1 equals a minus 1 plus 1 plus 1. A equals 2. Am I done? Nope. Because what was the point? Partial fraction decomposition. So I go up here and I say, oh, what was the point? To figure out where you could have come from. Or how you could get broken down. Decomposing body. Decomposing fraction. We're breaking down into its pieces. So whether you put A here or here doesn't matter. Because as you solve it, A will end up being the proper number that should go above whoever his denominator is. Some of you are like, how'd you know to put him first? It didn't matter. A is just something unknown. B is another something unknown. But in the end of the day, no matter where you had the A or B, you should end up with what over x minus 3? 2. And what over x plus 2? Negative 1. And isn't this what we saw yesterday worked? Oops, too far. Isn't this what we saw yesterday worked in order to get the original function? So yesterday they gave us the answer and we checked to say, oh yeah, makes sense. But then we ended class and you guys just finished off. How do you get from here to the partial fractions without knowing the answer? And some of you guys, that's something that you always have to work on for tests. Because in homework, you can kind of see where it's going and be like, oh, it makes sense. But as far as your brain making the jump of solving, that takes a little bit of extra work and practice. So let's cut this down into steps, okay? Short and sweet steps. Well, there's short and sweet steps, and then there's like the long drawn out, ooh, big old box of steps. Let's start with short and sweet. Okay. The very first step to partial fraction decomposition, the very first step to breaking a fraction or a rational function, ratio fraction, a rational function down into its partial fractions is actually something we didn't have to do on this problem. And it's a vocab term if I hear correctly in your homework. Divide when, now pause, improper. What have we heard improper before in math? Fractions. Give me an example of an improper fraction with a number in it. 11 over 5. Why is it improper? You can simplify it. That's one way of saying it. Another way of saying it is, isn't it top heavy? Why is it top heavy? Fractions are usually shown to show partial or parts to whole, right? But what's true about the part to the whole? It's bigger. How many 5s are in 11? 2. So there are 2 whole 5s in 11, and then there's how many left over? 1/5. So a mixed number says, okay, wait. That's an improper fraction because technically fractions are only supposed to show parts per whole, but you have 2 wholes. 2 wholes and then 1/5 extra. So when I'm talking about improper fractions now, I'm talking about improper functions. Function improper. Top heavy? Oh, so there's more terms on top? Not necessarily. The numbers are bigger on top? Not necessarily. What do you guys see? The degree is higher. Let me zoom in. I want to show it with the example, but this actual first step wasn't in this example. I'll show you why in just a second. Divide when improper. An improper function, an improper rational function, because it can't be improper if there's not a ratio, if there's not a fraction. A function that's improper has a numerator, that's just a subscript, a numerator degree that's higher. Now wait, you need to add something in for me. That's greater than or equal to. Not just greater than, or equal to as well. Now in fractions, that's also true. If I had 5 over 5, guess what? That's an improper fraction technically, because what is 5 over 5? 1 whole. So technically, 5 over 5 is improper and 6 over 5 is improper. So whether the top is stronger or equal to. That's with numbers, but with functions, we're not looking at numbers. We're not looking at how many terms. We're looking at the degree. So if I was to give you a few examples, just really quickly. Let's say I was to give you something like x cubed all over 100 minus x squared. If I was to give you 10 plus x squared minus 13x cubed all over x to the 4th. If I was to give you 100 all over x squared. Which of the following, 1, 2, or 3, which of the following are improper? Just one? All of them? Which one's improper? Why just the first one? What's the degree of the top on the first one? What's the degree of the bottom on the first one? Is the degree of the top stronger than the degree of the bottom? Yes. So is this improper? Yes. But why are neither, whatever you want to say, potato, potato, why are neither of those improper? But he has more terms. I don't care. What's his degree? He's a cubic. What's his degree? A quartic. Who's stronger? Bottom. Bottom wins. Not improper. Bottom wins. How about this guy? But he has 100 and he only has 1. But what's his degree? He has no x's. He has 2. Who's stronger? Bottom. Improper is only when it's top heavy, only when the top wins, and that has to do with the degree. But hold on, what do you see before the word improper? That was just to figure out the word improper. It says to divide. What? So that is improper. I'm supposed to divide. Before I do anything else with partial fraction decomposition, what does that mean? What do we do to divide? Now I'm going to actually rewrite it, negative x squared plus 100. What is this process called? Long division. Polynomial division, long division. So when I say when did we do polynomial long division? I want you guys to find a place in your notes that you can say reference page, boom. When did we do it? Can anybody find it? When did we do long division before? 2.2? What were we trying to find? Polynomial function? Is that when 2.3? Is that when we were doing oblique asymptotes? Oh, we were just doing division. Okay, so you guys can put down reference section 2.3 if you want. But can anybody find where we were doing oblique asymptotes? Horizontal asymptotes, weren't we trying to see who was stronger, the top or the bottom? So we were testing degrees. Oblique asymptotes, we would have to do polynomial long division if the top wins by 1. The title of the section should have been rational functions. What section is that? All in chapter 2 we talked about long division. So 2.2, 2.3, 2.6, lots of different places we did division. So if you need to go back and review. When improper. I'm putting it in green because it's review. Sections 2.2, 2.3, 2.6, lots of different places to review long division. But can you guys just remind me really quickly? What happens if I don't have a lot of stuff to put inside the box? You need to do zeros, right? And then how do we start off a long division? I'm not going to have space to finish it, but how do we start it off? Compare, right? How many times will negative x squared, or what times negative x squared will be x cubed? Negative x. Careful, right? And then when I go to distribute, remember, he's a binomial. When I go to distribute, I would get x cubed. Remember, you always want the first one to match. The next one, it just falls as it may. Negative x times 100 is negative 100x. I would put that in the x category. And then division, what do we always do? What operation? Don't kill a seal. Distribute your negative, right? Wait a minute. What happens when I can't go anymore? Because x squared times will never become x. Yeah, he becomes a remainder. What do we do with remainders? We rewrite him as a fraction. So if you ever start off with an improper fraction at the very beginning doing partial fractions, we can't go partial until we get out all the whole components. And then whatever's left, that's what we'll focus on for partial fraction decomposition. Now, why didn't we do this whole process of dividing on the example we saw yesterday? Now, granted, I did it fast, but why didn't I do any division at the very beginning? The bottom wins. It's not improper. It's already part to whole. It's already bottom heavy instead of top heavy. So I'm going to take what's already a partial and I'm going to break it down, or a part, I should say, and break it down into partials. So what's the difference between that and this? Top heavy, I need to divide. I need to get out the whole component or the whole piece first, and then I can deal with whatever's left over. I'm dealing with the remainder. Now, that's the first step, and that's a really loaded first step. But what comes next? Now I can compare this to the example we did yesterday. Okay. This one wasn't improper, so we skipped step 1. But now step 2, we're on the same page. Step 2, what was the very first thing I did? Factor. I factored x squared minus x minus 6. Let's give a little more room. There we go. I factored x squared minus 6 minus x, and I got x minus 3 and x plus 2. And what did I do with those factors? After I factored, I formed. Yep, I did the forms of the partial fractions. So I formed partial fractions for linear factors. Linear factors, what? Linear factors. Linear factors are the ones of the form x plus or minus, let's just do like a little a. Now, you can have technically a squared or a cubed or a fourth or a fifth or a seventh on the outside, but on the inside you have to have an x just to the first degree, like a line, y equals mx plus b. Whatever's going on the inside. And technically, if you want, you could have an actual little number in front of the x. You just usually don't. So if you want, and it helps you remember it a little better, you could do mx plus b, a line. It could be raised to a power, but on the inside, it has to be x to the 1. And for linear factors, we always get to put above them whoever we have. I'm just going to do some as an example. Maybe we have x plus a. Maybe we have little a, little c alone. Because the long story short is if we're making partial fractions apart already, its partials can't be top heavy either, meaning I can't have an ax or else they would be tied, and that's not working. That would have been dealt with in improper division. Or if I had an ax squared, that's improper. No. That should have been dealt with way up here. So I need the degree of the top to always be 1 less than the bottom. And that's when it gets weird, is when you have quadratic factors, because quadratic factors, or cubics, or anything beyond. But you're only going to see quadratics for me. What if you have something like an ax squared plus bx plus c that can't be factored? I don't care whether he's squared or cubed out here. But let's say it's one of those that only factors to imaginary numbers, like x squared plus 4. I could even show you that one. Let's do an example of, I'll do an example over here. What if we had something like x squared plus 4? Let's say I had x squared plus 4 squared. Let's say the common denominator was the squared guy. Well, I could have a single or I could have a squared, but the long story short is I can't factor him anymore. I could do a minus, but not a plus. If I try to square root 4, it's imaginary. So therefore, I have to not just put a because it needs to be improper. This one could be improper and still have an x term. This one could be improper and still have an x term. It's not top heavy if I have an x above an x squared. But it couldn't be an x squared or an x cubed, or else it'd be improper. So the improper has already been dealt with. Anything that's top heavy is already, or should have already been dealt with division way up here. With this long division, improper things are dealt with. So we're only looking at parts per whole. We're not looking at anything with whole components. So since everything is now proper getting into these steps, I have to make sure my partial fractions are proper too. So just a few of you guys might have realized in homework yesterday, did they show you any? Ooh, they did show you. They showed you one, and they even used the same one I did, where it wasn't just A's and B's or A's and B's and C's, but do you see now why they have a BX plus C? I couldn't have anything beyond an A or else it'd be improper. I couldn't have anything above a B or a C because all of those are, wait, but yeah, but couldn't I put parentheses around the X, and isn't it just X to the 1 that's being squared? Like X minus 0 being squared? He's actually okay. He's not, though. Because I can't possibly show parentheses with that being x to the 1. I can't factor him anymore. We have a special name for him. It's called irreducible quadratics, or irreducible polynomials, but we'll get back to that. Let me show you that big old box that some of you might want to study, might want to write down, might even want to take a picture of. Let me show you the big box, and let's see if it helps any of you at all. It's a lot of words. So I summarized it. Some of you might just want to skip it entirely, like look at it with us, but what do they say to do first? Okay, do they give the same detail that I gave? When improper, when the degree of the top is greater than or equal to degree of the bottom, divide. When you divide, you should get whole stuff plus fractional stuff, the remainder. Take the fractional stuff and do the rest of the process with just the remainder. It's basically what I showed, but with a lot more words. It's good. It's good detail. If you like it, go for it. If you don't like it, just use my short and sweet version. What does number 2 say to do? Completely factor until whoever is irreducible, until whoever can't go anymore and still be real. Got to keep it real in here, at least for right now. We already went imaginary earlier. So you go as far down as you can. I call it mx plus b. They call it px plus q, but go as far down as you can with factors. And they're allowed to be powers outside, but factor as much as you can inside. But every now and then you get stuck and you can't factor anymore. Oh, well, it is what it is. For linear factors, just single constants up above to keep it proper. But for quadratic factors, if you can't go down anymore, put all the rest of the terms. Guys, aren't my steps basically the same? Just shorter and sweeter. Some of you like the detail. If you do, take a picture, but I'm moving on. If you like the detail, take a picture. Otherwise, I'm moving on. Let's go play with another one. Let me get another picture. There's a trick? Let's not do the trick first. Let's just do an example. All right, guys, if we were just to do the steps, let's not make it a trick yet. We can get in trouble if we do tricks too fast and we don't understand the idea. So help. What would we do first on this guy? Why not divide? The bottom wins. We're okay. No division. So instead, what do we do? Ooh, it's yellow. That's awkward. Factor. All right. You guys already factored the bottom, right? What do you get? Does it matter if I wrote x plus 3, x plus 1, or vice versa? No. But why don't you write it the same way I did, or do that way all of our letters match up. But in homework, it doesn't matter. So who am I going to make when I'm forming my partial fractions? I can do A, and I can do, because aren't these guys just little linear? So if that's x to the 1, go down a degree up here, x to the 0. Okay, just A, just B. After you form your partials, now what? Multiply by that big old common denominator. But for some of you, just for some of you, multiplying by the x plus 3 times x plus 1 might get a little confusing in the distributing. So just in case it helps, another way of looking at this, if some of you got it from the example that we did at the beginning of class, just go for it. For the rest of you, what you could do is you could actually say, okay, I need a common denominator, so I need x plus 3 times x plus 3, and x plus 1 times x plus 1. If it helps you, you could get little baby common denominators, and then what happens to everybody? They all have the same denominator. So when you now go to multiply, maybe you can see, for some of you, it's just a little bit easier to see. When you distribute, everybody's denominator goes away. Everybody's denominator goes away. But whichever way you do it, you should end up with just the x minus 2 equaling a times x plus 1 plus b times x plus 3. However you do it. Now, what did you guys see me do in my example to finish, well, or to keep going on the problem? Look over there. Who do we have? Instead of reals and imaginaries, we have x terms, if it helps, and we have constants. Right? Who are my x terms? I have one x term on the left. What happens when we collect just our x terms? Don't you have 1x equals ax plus bx? Have we gotten them all? Yeah. We had an x term there, and an x term there, and an x term there. What does that leave us with? Who are our constants? Well, everybody else. Everybody else would be negative 2 equals, finish me off. stealing everybody else. Do you guys see how I separated? What can I do over here? Yeah, if it helps, you can factor out the x and say a plus b times x. Long story short, the x's don't really matter. What I care about is the 1 had to come from the a combining with the b. It just happens to be the same as last time. It's not always the same. You don't always get 1 equals a plus b. It just happens to be the same in this one. What can I do with both of these guys? System. Yeah. They could definitely be fractions. If they are fractions, what they would do is simplify the complex fractions. So they would be moving, say it was 1/2, the 2 would come on down next to the x plus 3, just to make it look nicer. Just a warning, that's how you're going to make it match with the answers in the back. Does that make sense? Now, guys, do we just have a system? Solving the system, what do you guys think? Just make this guy negative? Is that okay? A's cancel. Negative 2b equals, double check my math. It's a fraction, which is why Adam was just saying, can A and B be fractions? Yeah, because fractions are still constants, right? Well, stink. B is negative 3/2. Well, pause. Still back substitute. You guys all double checked my work, so we're doing okay, right? No one found a mistake. Sure? Okay. So go plug it in. I have 1 equals A plus negative 3/2. Don't I have to add 3/2 to the other side? You guys okay if I make 1 2 over 2 to make my life easier? Okay. I'm going to make 1 2 over 2. Adding my 3/2. Adding my 3/2. So A is equal to 5/2, right? Now pause. What was the end game? What's the goal? Getting my partial fractions. Yeah. Does that make sense? So we're going to come back to the beginning and be like, all right, who's going to go above the x plus 3? Who's going to go above the x plus 1? I go up and I say, my A. Okay, take your A and plug in. 5/2. And my B needs to go above x plus 1, so negative 3/2. Does this look fully simplified? And you're exactly right. So what would the back of the book have done? They would have said, well, let's simplify our complex fractions. Let's multiply top and bottom by 2. And you'll end up with 5 over 2 times x plus 3 minus 3 over 2 times x plus 1. So they would have done, whether they did the cool Uganda trick or whether they put this guy over 1 and multiplied by the reciprocal. Either way. They end up with their final solution. And you can't combine it because they're supposed to be separate and they're different denominators, but they just happen to both have a 2 in the bottom because they were both fractions. How do we do? Who did I lose? I see a lot of you guys boxing, which means you were pretty close with me. Did it kind of follow the other one? What went weird was the fractions, right? Okay. But otherwise, kind of the same. So what's different when I give you this one? Long division. It's top heavy. Because there are so many terms. No. Why is it top heavy? Because it's x to the 4th. But can you guys, even though there is an x to the 4th, I'm going to do the long division pretty quickly. If some of you can do it with me, that'd be awesome. But when I go to do the long division, what happens when you do the long division? Hopefully stuff goes away because you're going to have whole stuff that's in here right now that you don't really want in there. Right? So if I was to go ahead and multiply, say, by x, then my x to the 4ths match. That matches. Ooh, a lot of stuff is matching. Now, I'm not going to kill any seals. I'm going to be really careful. X to the 4th minus x to the 4th cancels. 2x cubed minus 2x cubed cancels. 6x squared minus x squared. 5x squared. Can we go any further? No. So how do I rewrite this huge guy. Five x squared plus 20x plus 6 all over x cubed plus 2x squared plus x. But what am I actually taking? Am I taking the whole guy to do partial fractions? No. Am I taking the whole answer to do partial fractions? No. Who do I split into partials? I need the fractional, just the remainder. So I'm going to hold on to this. I'm going to, oops, that didn't work very well. I'm going to remind myself, okay, this is the entire answer. This guy became this guy down below. But who am I actually looking for or looking at for partial fractions? That guy. So when I go to do my partials, I'm going to do 5x squared plus 20x plus 6 all over. Don't I need to factor? Huh. What does x cubed plus 2x squared plus x factor to be? Oh, pull out an x, right? X squared plus 2x plus 1. Oh, keep going. Uh-oh. Okay, hold on. Did you guys remember from the beginning of homework? Wait, pause. What would my partials be? An A, a B, and a C. Why not a CX plus D? Because look, he's a little baby linear dude. Guys, it's not going to have due until Thursday because I want to do some more examples tomorrow for at least half of class. But wait, if you don't start it by tomorrow, how much is tomorrow night going to hurt? So get to 16 and get a little bit further. Sound good? All right. Bye, guys. See you later. I'll change Google Classroom. I'll change Google Classroom. Yeah. Yeah. No.